So we would like to calculate the transport properties of this Anderson system, and last time we defined this Hamiltonian in the presence of a small vector potential. And so we know from the beginning of this course that once we try to calculate this transport, we need to couple the system with the vector potential. For example, this A, vector potential A, is coupled to this current operator J, and then we can actually do perturbation theory on this average current and in the presence of a small vector potential to linear order in A. So that's called the linear response theory. And this J is called the paramagnetic part of the total current operator. So the total current operator, capital J, is given by this little j subtracted by this charge density N, electron charge E, and vector potential A. So remember, this little j in quantum mechanics is defined by this. Of course, it's h bar, so then in the Heisenberg picture, so we know this H external, which is the external Hamiltonian, which is the vector potential A coupled to this paramagnetic current operator. In the Heisenberg representation, so it is given by this time evolution operator, e to the IHT and e to the minus IHT on both sides of the x external, and the current operator is related to the Schrödinger operator by the same transformation. And this was a homework problem that you can show the current operator in momentum space is given by this. Suppose we can Fourier transform this psi from the real space operator to the momentum space operator, with A and A dagger, the operators in K space. So that's the background. So we need to derive this linear response function for this current operator. So let's just start from the Schrödinger equation for psi of RT, and we know that this is the solution. The solution is that this time evolution of this eigenfunction, the Schrödinger wave function, is given by this time evolution operator e to the minus IHT, where h is kind of a non-interacting part of the Hamiltonian, and times this u external, where u external is just our unitary operator that we solve, or S matrix, and times this Schrödinger time-independent part of this wave function. Where this u external is given by 1 minus this integral. Anyway, this derivation follows exactly the same way that we did for this S matrix. Remember this S matrix and in the interaction picture. And this u external of t is just approximately given by the linear order, this integral. 1 minus I times this integral, which contains only the linear H external operator, because we simply just take this, the first order approximation. So you just plug that in, and you take the average of this total current operator, which is given by this kind of expression value, minus NE of A. So you simply just plug that in back to this. So this is the full solution of this Schrödinger wave function. And you just plug it in here and there, and you will get the following. Capital J average is given by this little j average plus this commutator between H external and little j. So then you simply just plug in this H external, which is this guy here. So it's an integral over A dotted j. So then you simply just get the current commutator between these two currents, which is the current correlation function. So this capital J average is the expression value of the total current, and the small j average is the paramagnetic part of the current, expression value of current, and this total current, capital J, contains both the paramagnetic part of the current and the external potential, vector potential part of this contribution, which is the second term here. So you simply just move this little j average to the left-hand side of the equation, you get the deviation between the total current and the paramagnetic part, which is zero field current, expression value of the current, and this deviation, is actually linearly proportional to this vector potential A, and so we will just derive that in just a moment. And then this deviation, is actually proportional to the current correlation, which is the commutator between these two current operators multiplied by the linear operator A of t. So let's take a short break. When we come back, we will formally derive everything.
Excuse me, what we call so-called the paramagnetic part?
The paramagnetic part refers to the fact that there is no vector potential. Suppose there is no vector potential, A is 0, then capital J is the same as little j. And that defines little j, which is the current operator in the absence of the vector potential. Okay, so let's take a short break. Any other questions?
Another question is, here we didn't choose any gauge.
Yeah, we don't need that because this is, so you'll see that this deviation in current operator simply doesn't matter which gauge we choose. It's just a vector potential. That's all. So we will finish this Anderson localization problem probably after 2 or 3 hours of lectures, and then we move on to the Coulomb interacting electron gas and electron phonon system and the BCS theory. So hopefully we will cover all the topics by the end of semester.
What kind of so-called contour Green's function do you think is important?
Contour is important when you really want to calculate analytically the Green's function. Of course, I understand that the first principle of density functional theory is another possibility to calculate this self-energy or full Green's function. There are pros and cons, with advantages and disadvantages in either approach. So this more analytical approach, by doing this contour integration, has this advantage that you know what you are doing, and because you could analytically get the Green's function and you could see their contributions to all the observables directly, by plotting this real or imaginary part of the Green's function, and you know where the poles are, and you know the spectral density, and you know everything analytically. So this helps us to gain analytic understanding of the problem. In particular, in some simple systems that we can analytically solve this Green's function. Of course, in many body systems, it's really not easy to solve everything analytically. And in some cases, some numerical approaches are necessary. So, for example, this Anderson localization problem, electron phonon coupling, or BCS theory, we don't need density functional theory to understand those physics. And that's the power of this contour integration approach to the Green's function and so on. And of course, I think we cannot have exact solutions in all these many body systems, even in the simple cases like electron phonon coupling and so on, or BCS theory is just some kind of approximated solutions. But even we made approximations, and if this approximation are reasonable or accurate enough, and it's really helped us to gain a much deeper understanding. So in many cases, I think we don't need exact solutions. We just need approximated solutions. That should be good enough. If you really want to solve everything exactly or numerically accurately, and there's a price to pay. And the price is that, for example, this density functional approach, you really lose this connection to this Green's function. So what is the key players in the Green's function? Or what are the main coupling that will lead to the features that you want to study? You simply lose contact with all the details. Anyway, so we'll come back to this later. So let's just try to subtract this capital J average by this little j average. And we could find that this is given by this integral. This alpha beta refers to some, this directions, say x, y, z. And this capital P R alpha beta is defined as this current correlation function, and there's a constant delta function. So sometimes in some reference books, they define this P kind of a correlator. The first term is the current correlator. The second term is simply just a constant times delta function. So to distinguish between this left-hand side capital P quantity, and I put the bar on the right-hand side of the P alpha beta. So you can see that this quantity, which is the deviation between this expectation value of a total current and the paramagnetic current, which is called response function, or response of this external vector potential. So delta J is linearly proportional to this vector potential A with some prefactor, and this prefactor is given by this current correlation function, and minus this constant times delta function. And this is what we will do, because later we'll derive this electrical conductivity is actually linearly proportional to this delta J. So suppose that this Q is 0, little q, which is the momentum transfer in Fourier space. So we concentrate on this uniform electric field. Remember that this from electromagnetic theory, that this electric field could be generated by time derivative of the vector potential. Remember, on electromagnetism, and in this frequency domain, this electric field as function of the frequency or AC field is actually omega times A of omega. So of course it's some prefactor which I don't care. So the point is that this in the AC field, this electric field is actually linearly proportional to this vector potential in frequency domain with this omega as a prefactor. So this allows us to Fourier transform this delta J from RT to Fourier space omega. Of course, under the condition that this q, little q is 0, when we perform this Fourier transformation from the real space to the momentum space, this momentum is fixed at 0, which means that we simply just calculate this uniform or average, this current operator. So we can define this delta J as function of omega, which is this quantity plus this capital P bar and dotted capital E. So you can very clearly see that this capital E as function of omega is actually given by omega times this A of omega. So you get one factor of omega, which will cancel by this omega in the denominator. So you go back to this Fourier transform of this equation right here. But to write this equation this form, we could very easily identify electrical conductivity, because this is what we know. So from classical electromagnetism, we know that this J is given by sigma times electric field E, where the sigma is the same sigma here, which defines electrical conductivity. Okay, so here in quantum theory, we can also define such a relation between this current or average current and the electrical field. So this is the quantum version of the electrical conductivity. So if we don't have any external field, I think there's no response. So there's no delta J here. So this delta J here is the consequence of this external field that we apply.
The E had a sub beta electric field.
Of course, you could consider you apply the field along the x or y or z direction. So alpha and beta is simply just your x, y, z. So you could see that we need to actually project this p alpha beta onto this a beta. So you could define this static electrical conductivity when omega is 0, and suppose we just probe this xx component of the sigma omega 0, which is this one. So the static electrical conductivity is actually the real value quantity. So in other words, we need to take the imaginary part of the pxx, because there's an I here. And this is what we will do, that we first will need to calculate this p bar alpha beta as function of omega, and either we take limit when omega goes 0, or we keep this omega as finite, and we take the imaginary part of the p alpha beta, and this quantity will be proportional to the sigma alpha beta. Okay, so let me just rewrite this p bar alpha beta. So the capital R in the superscript here represents this retarded component of this current correlation function. So in general, this p bar alpha beta is actually a tensor, which we call this conductivity tensor. The reason why this is a tensor is because there are two different directions that we need to distinguish. The first one is the current flow direction, which can be either x, y, or z. Another is the direction that we apply the vector potential. Okay, so this capital E is the electric field, which could also point to any direction in x, y, or z. So this alpha may or may not be the same as beta. So you could apply electrical field along the x direction, but what you measure is deviation of the current along the y or z direction. Okay, and that's why you get the sigma alpha beta like this. This means that we could apply the field along the direction of beta, but what you try to measure is the current deviation along the x. And of course, the sigma alpha beta, which depends on both the alpha and beta direction. So that's what we call this conductivity tensor. Right, so one more remark. So suppose we don't apply the magnetic field. Suppose in the absence of the magnetic field, and we know that this is 0 if alpha is not the same as beta. And this is the case that we are interested in. So then in that case, we only have the diagonal matrix element. You can imagine that we could apply the vector potential, which leads to both the electrical field and magnetic field. So remember from your EMN, the magnetic field is given by what? The curl of A, right? Which means that if the vector potential is a function of R and the curl of vector potential is non-zero, in that case you get the magnetic field, and then you get both diagonal and over-diagonal elements of this conductivity tensor. But we don't consider that case. We just consider a very simple case that you apply the vector potential A, which is not the function of R, but only the function of T. In that case, you only get the electrical field and no magnetic field, and so you only have this diagonal elements of the conductivity tensor. All right? Okay, so and this formula is the one that we should follow in the coming calculation. So we will calculate this current correlator in this Anderson localization problem, and we will first just try to plug in this full Green's function, including the self-energy corrections, in that current correlator, and we'll do it by a complex analysis, and then we will find this Drude conductivity that we already learned in the classical electrodynamics. But then we should go beyond the self-energy and by considering so-called vortex correction. And once we include the vortex correction, and we'll find that this localization occurs in a low-dimensional system. Okay, so but let's just try to do it in a simple way, which means that we try to evaluate this current correlator by including only the self-energy of the electron propagator. Okay, so let's take a short break. Okay, so let's try to calculate this current correlation function. So I put the time order operator here, and this is the diagram in frequency domain. So we don't Fourier transform this real space, but we Fourier transform this time to Matsubara base, and you immediately see that this frequency conservation is satisfied here at R and R prime. And since the current operator is actually proportional to this psi dagger gradient psi, right? So if we have this, the product of these two current operators, so you have four operators, so this psi dagger psi, psi dagger gradient psi, right? So, and you can form a loop made of fermion propagators. Of course, it's a gradient operator, so we will take care of this gradient later. So we can form a fermion loop like this if you simply just expand this current correlation function. And in Matsubara frequency domain, we could write down this expression for this diagram, which is simply just given by this product of these two Green's function, G italic, but a different frequency dependence. So the first one is the propagator up here, which carries frequency omega m minus omega nu. Omega nu is just external frequency. So, but the second one, the lower one, carry this Matsubara frequency omega n. Okay, so we need to sum of this internal degrees of freedom, which is the Matsubara frequency omega n, which appeared on both propagators. Okay, so remember previously when we do this, we could transform this summation over Matsubara frequency and also this 1 over beta prefactor into a contour integration, and in that contour representation we try to encircle this poles which appears along this imaginary axis. And since this omega n is a fermionic multibar frequency, so it should be generalized into f of z, where f of z is simply just a Fermi function-like function, with the z is a generalized variable, which is a complex variable. And when z becomes this I times omega n, and you get a simple pole because this denominator vanishes, and as a result this is simply just sum over all this pole along this imaginary axis. If you simply just perform this contour integration along this red path, and you simply just go back to this Matsubara sum. Okay? But of course we will do it differently. So instead of circling around this vertical axis or imaginary axis, we should transform or deform this contour like what we did before. Okay? Because we know very well that this G is actually 1 over I omega minus epsilon k, and also sigma, which is the self-energy. And when you perform this contour integration, so you will hit a pole either at z equals to epsilon or epsilon plus I omega nu. Suppose we don't care about this sigma at the moment, or we simply combine these two. Okay, so anyway, you'll see immediately that there are two poles. One appears right here along the x-axis, where this is x-axis, right? So, or energy, some energy, frequency. And when we hit the pole at epsilon, and this is simply the pole of the lower Green's function. But we can also hit a pole up here by shifting epsilon by plus I omega nu amount, and we will hit another pole right here. Okay, so this is the pole for this upper Green's function. All right, so then to take advantage of these two simple poles appearing on both propagators, so we could deform this red contour to actually encircle both simple poles marked by yellow. Okay, so this is the strategy that we should deform this contour to enclose these two yellow poles. Okay, the way that we change this contour is the following. So let me just sketch the contour deformation, and we know very well that there will be two simple poles at different places, right? Okay, so right here and right here, epsilon. As a result, we first need to actually deform this contour in such a way that you do it like this. You actually encircle three parts of this poles along this imaginary axis like this. Of course, this contour both below and above the axis actually extend to infinity. Okay, so imagine that this actually go to plus or minus infinity of the imaginary frequency. So then you need to deform this one more time, because you need to deform the contour in order to actually encircle this two pole, right? So how do you do that? Okay, so you should simply just flatten this part of this red contour when it gets close to this yellow straight line, horizontal line. Okay, so what you can do is to actually right here, so you should insert this upper and lower part of this contour right above and below these two yellow lines. Okay, actually add this part of this contour, and you try to connect this. Because remember, when we deformed this contour previously, what we did is do what? Actually, what we did is something like this, right? Right? So, and we will do that in a similar way. So by adding this horizontal part of the contour and try to actually stretch this red part of the contour along the yellow lines, and we will get the following contour. Okay, so this is one, this is another, right here, and there are many pores right here and there. Okay, so in other words, we try to stretch this part of the contour along the horizontal axis directions so that you form a semicircle on top and bottom part of the contour, but then you will leave behind a rectangular shape of this contour in between these two yellow lines, right? So you can imagine that you could do that. Okay, so I could deform this oval shape of the red contour into the box, which is this box. And I can form a semicircle here and also down here. Okay, and this is precisely what we're doing right here. And remember, these two yellow poles here and there will be accessed if we take this orange contour. Okay, so you will need to evaluate this integral very close to these two yellow poles. Okay, so then we could simply just decouple this Matsubara sum into different parts of a contour, the upper hemisphere and lower hemisphere and middle box. Okay, and then we could distinguish different parts of the product of the Green's function. Okay, and in particular, we will know whether this part of this Green's function along any horizontal contour is actually retarded to the advanced part of this Green's function. So then we'll form many products, the sum of the many products of these two Green's functions along this 1, 2, 3, 4 contours. Okay, and by the same token that we showed earlier that all the other parts of the contour don't contribute for the same reason, that you get convergence factor, so that all these boundaries of all this contour are 0. Okay. Okay, so we don't care about all these different parts of the boundary contours, which automatically give you 0, and we only care about these 4 horizontal lines. Okay, so then we could rewrite this contour integration. So let me just rewrite it. So this is given by, okay, so we have two different parts of the contour. One is along the upper yellow line, another is along the lower yellow line. Okay, so along the upper lower yellow line, the integration is between minus infinity plus I omega nu, because this is the location along the y-axis, which is the imaginary axis, and this is at I omega nu. So there's a shift along this imaginary axis for this upper contour by I omega nu, and the integration is between minus infinity plus I omega nu to plus infinity plus I omega nu. Okay, and we will look at the sign plus or minus sign later, but inside this bracket we get what? We get from the left to right and minus from the right to left, right? So there are two contributions. One is from minus infinity to plus infinity, another is plus infinity to minus infinity. So we actually reverse the sign, the second part, because this comes from the right to the left. And each term we get the product of the two Green's functions. The first one is the upper propagator, and the second is the lower propagator. So the upper propagator carry the frequency, or this variable z minus I omega nu, because you generalize this I omega n to the complex value z. So then in the complex contour variable, this g is a function of z minus I omega nu right here. And the second one is simply g of z. And likewise, the second contour, you can also label this frequency dependence or z dependence right here. And similarly, the lower yellow line, contour, you could also follow the same way to actually rewrite this in terms of these two terms. So now let's just discuss the plus and minus sign right here. So this g plus and g minus is actually defined by the sign of this argument, the plus and minus sign of this argument of the imaginary part of z. G plus and g minus defined by following rules by the argument of g of z. So in other words, by the sign of the imaginary part of z. So if this is positive, then g of z is called g plus of z. But if imaginary part of z is negative, then this is g minus. So later when we perform the analytic continuation, and you'll find that this g plus will be g retarded and g minus will be g advanced. Okay, so let's just check the plus minus sign of this Green's function. So for example, let's check this argument right here. Suppose we have g plus z minus I omega nu. The way that we check the z is by this pole, right? So this pole occurs at epsilon plus I omega nu plus I eta for this Green's function, g z minus I omega nu, and the imaginary part of the z at the pole is actually positive. And as a result, we call this g plus and so on and so forth. So you could very easily see this. For example, this g plus z along the first contour, this is g plus z minus I omega nu times g plus of z. So let's just try to analyze the plus and minus sign of this g of z along this first, the upper contour right here. Here z, epsilon plus I eta, right? Epsilon plus I eta. So this g of z, remember, come from this Green's function. And this Green's function gives you this pole at what? Epsilon plus I eta. And the reason why this is plus I eta is because this is right above this yellow line, right? So this is plus I eta, and this is minus I eta. Over here, this is plus I eta, and this is minus I eta. So then we could easily attach plus minus sign to all these Green's functions. So you could easily check the signs of this different pairs of the Green's function along these four different horizontal contour paths. As I mentioned, this contour integration could be actually done by deforming this, say, contour along this imaginary poles, and by extending this contour to access to the other two poles in this, say, complex plane. One is in the real axis, another is the pole. Just shift this real axis pole by I omega nu. And we could perform this analytic continuation from this multiplier frequency to the real frequency like this. When we do so, this G italic plus becomes the capital G retarded, and G italic minus reduces to capital G advanced. And so now the frequencies are the real frequencies. This Fermi function now reproduces the actual Fermi function that we are familiar with. And so these are the final expressions when we go back to the real frequency domain. Remember, there are four terms. The first term is the GR-GR, the second is GA-GR, and third term is GA-GR, and final term GA-GA. We could combine these two cross terms between GA and GR in the same variables by changing a variable. For example, you could shift this epsilon by omega, and then you could actually get the same expression for this product between GR and GA. But the price to pay is that you get two different Fermi functions at different energies. For the other two, we don't do anything. So we don't have time to prove, but you can check the textbooks that the GA-GA and GR-GR terms do not contribute to the integral. And so we only need to focus on this cross term, GR-GA term. Okay, so there are two terms, but we can combine these two terms in a single term. Okay, so we're almost there. So let's just use this kind of result, and we plug in back to this sigma xx. Remember, this is what we try to evaluate, right? The static conductivity sigma mu mu omega 0 is given by this. You need to take imaginary part of this p alpha beta, remember that. This f function is the Fermi function. Okay? So remember there are gradients in front of this current operator when we define this p alpha beta. And therefore, when we calculate this current correlation function, there will be a special derivative d by dr acting on this Green's function. Okay? There are two Green's functions, right? So one is this one, another is that guy, the gr and ga. Remember, this comes from this current correlation, right? So, yeah, and the current operator, there is a gradient. Okay, so, and of course, there's some steps, intermediate steps that you will derive this expression. Okay, so we also need to take this disorder average, right? And this is disorder average. Immediately, that when we take this differentiation respect to this r, you get the momentum, p mu prime. So, and this is all we need to do. So we know this capital GR and capital GA, right? So by including self-energy, so we simply just plug this in, and we perform this integration, and we get sigma mu mu. As simple as that. But we need to take the average, disorder average, for all impurity configurations. And we need to do that, perform this. Okay, but we already did the single capital G Green's function by taking the disorder averaging already. So this will not be a problem for us. We can simply just plug in this capital G bar and capital G A bar and capital G R bar, where this bar refers to this Green's function after disorder averaging. So we simply just plug in what we have obtained earlier, and we could evaluate this static electrical conductivity. Okay, so let's do it. Remember, this G retarded and G advanced is given by this, right? Or omega plus or minus I over 2 tau, where tau is the mean free time. Remember that, okay? And 1 over 2 tau defines the imaginary part of the self-energy, right? Okay, so we have done that. Okay, so we simply just plug this in and evaluate this stuff. Okay, so let's just do it. And this is called the self-energy contribution to the electrical conductivity. Diagrammatically, we could use this diagram to represent such scattering processes. Okay, so all these dashed lines refers to this disorder potential, and the cross term, these crosses represent all this interaction at this point where we already took the disorder average. Okay, so suppose we could simply just use a double line to represent such full Green's functions by including the self-energy of the electron propagator that is to be evaluated in this bubble diagram for the static electrical conductivity. Good. So then we simply just plug this in back to the sigma mu mu. And remember, there's a factor of 2 pi I here in the denominator, and we should take the imaginary part of all thing. And here is the factor of I and another I, so I times I is actually -1, so it's real. We take the imaginary part of the function, and this function shows the prefactor of 2 pi I. As a result, what we need to do is take the real part, not the imaginary part, because there's I here. Imaginary part of the I times the function is actually the real part of that function. Okay, so we take the real part of this integral. So then we need to take the static limit. Okay, so we have a triple integral, right? So it's dp, dp prime, and d. Energy, and inside the integral we have this complicated functions. The difference between two Fermi functions divided by omega, where omega is the difference between these two energies. And also px and px prime, and this g retarded times g advanced. But in the limit of omega goes 0, so this difference in Fermi energy divided by omega is nothing but the first derivative of the Fermi function with respect to energy, which is nothing but minus a Dirac delta dip. And we could change the variables when we perform these two, say, moment integrations. So we could use the polar coordinate. For example, this px is actually this Fermi momentum pf times cosine theta, where this theta is actually the angle between the x-axis and your momentum. And this momentum p and p prime are very close to Fermi momentum because at low temperatures all these electron states are very close to Fermi level, and therefore this projection is what is p f cosine theta. And effectively, you can change the variables to integrate the states near the Fermi surface, but you only need to integrate over this theta. Okay, so we change the integration variable close to Fermi surface by such a substitution, where the integral over d-dimensional momentum variables is actually approximately given by the density of states at Fermi level times the energy integration. Okay. And then we plug in this capital G retarded capital G advanced by this Fourier function that we obtained and derived previously. Okay, and this is the static limit of the electrical conductivity in the presence of disorder. And you will find that this static limit of this conductivity recovers Drude formula that we can even derive without quantum mechanics. It's a classical conductivity of a charged particle, okay, in the presence of this vector potential, or AC field, and which we call this Drude conductivity. Okay, so let's take a short break. But of course, we should go beyond this static limit, and in general, you can imagine that at finite frequencies, we could also evaluate sigma xx, right? Okay, at any given external frequency.
Which I have maybe it's a stupid question. In general, we have a Fermi loop. We need to have a times -1 for that.
Yes, but this -1 has been taken care of if you check the sign. Okay, so let's derive the static conductivity by plugging this G retarded, G advanced Green's functions and evaluate this theta integration and energy integration, where this G retarded and G advanced Green's functions give you this energy denominators, epsilon plus minus I over 2 tau. And you could use, again, this contour integrations. We know that there are two simple poles. One is on this positive imaginary axis, another is the negative imaginary axis. And you could choose this contour semicircle properly so that you won't get any divergence, and the correct choice is the upper hemisphere. And you pick up this pole right here, a plus I over 2 tau, and then you could simply just derive this static limit of this electrical conductivity in the presence of disorder, but you only include the self-energy corrections. And this is given by this E squared times square of the Fermi velocity times mean free time times density of states at Fermi level. So you could simply just relate these three quantities, Vf squared and tau and density of states, say in two-dimensional metals. And you know very well from the solid state one that this number density, little n here, is related to this kf squared divided by 4 pi, which is given by this. And as a result, this Vf squared is actually 4 pi n divided by m squared. And you know very well this capital N density of states at Fermi level for a two-dimensional electron gas is a constant, which is the mass divided by 2 pi. But the mass is electron mass. So you combine all these relations, you get a simple relation that is Vf squared times density of states at Fermi level is given by 2 little n divided by m. Okay? So you plug this in back to this formula, and you get the famous Drude conductivity for a classical electrodynamics, which is the charge E squared times the number density of your charge carrier times the mean free time divided by the mass of electron. So, and this, you can actually reverse this, you get electrical resistivity, okay, which is the reverse of the sigma xx.
Professor, well, the Green's function, I think the mass is a bare mass, right? But here, if the true conductivity, I think the mass is probably the effective mass.
Well, this is the issue that to be discussed. Of course, we don't renormalize the mass at this point, but in a simple case like non-interacting system, the classical, the mass is a bare electron mass as well. But you could consider this interaction effect is to renormalize the mass of electron from the bare mass to the renormalized electron mass, m star. Okay? But in any case, this general formula is actually the same. Okay? It doesn't matter whether the system is actually non-interacting or interacting. And for interacting, you simply just renormalize the bare mass to get to the m star. That's all. Of course, here, the m is actually the bare electron mass, but it doesn't change the general form of the true conductivity. Okay? But then this is not a big deal because we simply just recover the well-known classical Drude formula. But what is non-trivial is that we will consider a different type of corrections, which is called vortex correction. To this bubble diagram, remember the bubble diagram. So, but this vortex correction will lead to a dramatic changes in the static conductivity in low dimensions. So let me just remind you this Drude formula. In classical EMM, remember, suppose we have a classical charged particles under the influence of the scattering and Newton's second law. And this is definition of the electrical conductivity in classical electromagnetism. And in the presence of the scattering, we define the average scattering time or mean free time tau. And Newton's second law now becomes this kind of equation, including this scattering time. And then we can define this current in the classical EMN, which is the number of charged particles times the charge E times the velocity. And so, but the velocity could be converted into the electric field, and that's the prefactor in front of this J and E, which is the Drude conductivity, sigma. Okay? So from the classical Boltzmann equation, we could easily derive such an expression for conductivity. Okay, but what's the big deal? Well, the big deal is that we could start to think about other corrections, and that correction will lead to a very different dramatic changes. Okay, so remember, so far we only consider this type of correction, which is a self-energy correction on the electron propagator. But there's additional corrections. We'll continue discussing this vortex correction next time. Okay, so but let me just very briefly introduce this kind of vortex correction. And this correction actually corrects this vortex point right here, and which is kind of the link or the scattering between electron in the upper propagator and the lower propagator. So the self-energy only renormalizes the same propagator, either up or down or top or bottom, but the vortex correction actually linked one of the electron in the upper propagator, another is a lower propagator. So, and in fact, it actually renormalized this part, which we call this vortex part. And you can imagine that we could have many contributions like this, which is the scattering of the electrons between two different parts of the bubble. Okay, so we will discuss that contributions next time, and this vortex correction turned out to be critical to understand the Anderson localization problem. So, and this vortex correction cannot be understood if we don't use Green's function. So there is no way that we can understand Anderson localization problem without using Green's function method. Okay, so this is not something that we could understand in the simple, say, solid state 1 without employing the Green's function. Because the vortex correction will not appear if you don't compute this kind of a diagram like this way. Okay, so that's enough for today. Okay, so we'll continue next Monday.